noticed is that there's a huge chasm between the performance people actually really get and what they're actually capable of. In many cases, it's orders of magnitude. Okay? Literally, things are running 1,000 times slower than they should be on exactly the same hardware. Okay? Now, when you're 1,000 times off, you've got to ask yourself, you know, is it me, or is it the hardware, or is it the database? And really what it comes down to is very often one of philosophy and one of approach. And we tend to see basically three core fundamental mistakes of philosophy or approach done wrong. Okay? So if your job is like me, you manage performance engineers or people who claim to be performance experts, just figure out which mistake they fell into. Okay? Are they using the tools and the products correctly in the manner they were meant to be designed? You know, remember people hitting screws in with a hammer? Is that the right way to use a hammer? We should be using a screwdriver. I see this a hell of a lot. Using the database and other tools in a manner that they shouldn't be used in. Okay? The next one, we call it the sort of the big data, little data design challenge. Okay? If you were designing something to handle 10 rows, would you code it the same way if you're coding 10 million rows? Everyone goes, no, that's obvious, you wouldn't do that. But how many times do we see a method being invoked in a tight loop 10 million times? And then you're having a performance problem. Okay? This big little data challenge, the design problems are getting worse and worse because the length that you need to iterate the same method over is getting longer and longer each day. It's a big deal. And the other one is one, particularly when you're in the triage space and you're trying to fix things, or what a lot of people call is tuning, which I think is an awful word. Tuning has become a synonym almost for hacking, you know, guessing. Okay? How many people in their lives have actually moved to a solution before they understood the problem? It might have sounded great in the meeting. You know, you may have scored lots of points with your peers saying, oh, we should try partitioning or something like that. But did you actually know how much payback it was going to give you, and was it going to fix the problem? Okay? How many people have made things go faster by changing things that they didn't understand? How many people have made things slower by changing things they didn't understand? You get my point? Okay, this is a big problem, this jumping into a solution. Very often what sounds good in a meeting or a conference call, but no numerical data to back it up. How many people do tuning by bit flipping? Just go try and turn this parameter on and off and see if it goes faster. Okay, we all do it once in our lives. We then learn not to do it, but it's kind of a career development thing. Okay, so that really is what we sort of chase down. Well, those who were there yesterday learned about SQL with John and I. Today we're going to talk about the dilemmas that programmers and architects have to deal with when they're architecting middleware-based solutions. And we're going to talk about what makes data big tomorrow. Other plug for what we do, we'll also be in Europe next year. Myself, Tom Kite and Graham will be doing our real-world performance day, and I think we're going to get some of what we learned this week incorporated into that day. And that's how that day can be arranged ad hoc through your own local user group. You probably need to book us about 8 months in advance, but you know, it's just getting Tom's availability. You know, we're just fixing performance problems. But what we also do, and we're starting to roll out, is actually a class. A long time ago, I was very naive, thinking that if we trained other Oracle people how to do real-world performance, they would be able to train other people. Well, it didn't kind of work out that way. So we're kind of changing the model such that we do a real-world performance course, basically when people can organize the logistics for us, which is usually a room, food, internet connection, and a computer and things like that. We'll do it on request. What we try to do is fill the room with as many people from our partner organizations, our customers, as well as Oracle internal. And it's really such that we can get the messages and the techniques out there. And the class is taught by, not by instructors, but by people in my team. And it's very sort of demo-orientated. We try to get rid of PowerPoint as much as possible. And it's also hands-on. Okay? We get you on the machines, and we get you some challenges. One of the examples we do is for OLTP, we have you on a flight simulator. We start injecting faults into a system, and you've got to figure out what it is. Boy, do we get some great answers. Lots of people jump into solution space before they've actually figured out what the problem is. Okay. Feedback from our friends at Turkcell. They came along to the class, and they were fantastic. They fell into every trap we set for them, one after another. It was fantastic. But great group of people. Okay. We're also available on YouTube, and we're going to try and do more and more stuff on YouTube. So the demos you see, when we eventually find time, we're going to record them up so that you can use them to augment your arguments with each other. Okay? One of the reasons we build all these demos is we got tired of arguing. How many people are tired of arguing at work and not getting your own way? Okay, we got tired of arguing with people and nothing happening. Okay, so if I see a problem that happens twice, we build a demo, and then the argument's over. Okay, how many people have seen our connection demos already on YouTube? How many people have used it to solve an argument? All right, it just cuts the noise level down, and gets it back to facts. And on that note, I'd like to turn over to Greg.
Right, so Andrew was asking how many people said they'd seen the connection demo before? Okay, some, but there's quite a lot of you that haven't. So, let's talk a little bit about what we've got here on our demo screen. So, demo that we're running, we have our configuration up here. You can see currently we've got this set up with connection pool, which is 96 connections to the database. We're running this against one node of a 3-2 exadata. The other screens that we've got here, this is showing the database response time in red. You can see that's just a bit over 2 milliseconds. And time spent queuing in the middle tier, application tier. Transaction throughput here is about 32,000 if I can read it from here. Activity in the database, green CPU, right? Just like the EM performance pages. And how busy the different machines are. You can see we've got the application servers and the database node there. Right, so the basic premise of the connection demo was that the number of connections that you have to the database should be a relative number based on the number of cores that you have running the database. So this is a 16-core box, and we've got 96 connections to it at present. Now, most people, when they're running an exadata node, aren't going to have 96 connections. So, Kai, maybe we can see what happens.
We should also point out, this is a system that's running really well. You notice how steady it is? You see how uniform the response time from the database is? Right. It's a straight line. And we've got a little bit of queuing in the middleware. Right,
so this is normally where the middle tier guys are saying, well, we're getting queues in the app server, so we need more connections to the database. Right? That's going to... Why do we need to queue?
Well, who's heard this argument? You're making me look bad. You're making me look bad. I'm queuing in the middle tier. I've got to throw it down to the database as fast as possible. So what we're going to do is we're going to open up the connection pool.
And we're going to open it up to 4,000. We're doing it by setting the maximum pool size, so we're not changing the initial. And so now the connection pool will grow dynamically.
How many people have got dynamic connection pools on their app servers? How many people have learned?
Right. Well, you can see it didn't take long to have some effect. Did it have the effect we wanted it to have? Yeah. We were trying to reduce the wait time in the application servers. It's not really what happened, is it?
So you'll notice that we've jumped from 96 connections to over 2,000 in about 3 sentences. Okay. That's how quickly. This is akin to a connection storm. How many people have tolerated and survived a connection storm? You've just seen one. Okay? Look what it's doing to the database at the same time, and the database response time.
And look what it's doing to the host too. So our database host is now completely pegged. That's running at 100% CPU.
So it's kind of weird. We've made the database CPU busier, the response times have got longer, and we're getting less work. What's
Anybody
wrong with
think
this?
that's a good thing?
Anything wrong with that picture? Okay. And you can see it's now becoming quite erratic. But what you have noticed, we're starting to eliminate all the blue. The app server guy has achieved his objective. He's totally eliminated waiting in the app server.
Yeah, unfortunately, from the business point of view, he's also significantly reduced the transaction throughput that this system is doing. Right? So from the business point of view, this system's now running in a much worse condition.
So his real-world performance is degraded, he's met his objective, and it's now more unreliable, and he's probably having people screaming at him at this point.
Right. Yeah, and one thing to remember about this is that application middle tiers were originally created to do queuing. There's nothing wrong with queuing there.
So let's get the queues back in again, shall we?
Yeah, so let's drop it back down to 96.
Get it back to 96. I can't bear to watch this much longer.
Just a quick point of feeling the kind of bad guy in this at the moment. Your database is letting through these connections, so you could be throttling the number of processes if you wanted to, something like that.
Yeah.
So you could
Yeah, so the question was, you could throttle the number of processes.
We could potentially throttle it, but remember this is an application where the response time is in the milliseconds. I don't know anything in a computer science that can yield fast enough and shift the context fast enough. Do you understand? So when you're doing these basically very fast OLTP transactions in memory that are happening sub-millisecond, do you think a scheduler can yield a process and react fast enough?
No, I wasn't rejecting that. I was saying presumably you must have the number of processes on databases, 5,000 or whatever it was. Maybe if you were concerned about so many connections coming through, you could set it to...
Yeah, but then you wouldn't be able to get this in as a DBA to debug it when it went wrong. So let's not think of it like that. So moving on, we kind of might make the point that getting the middleware right has a huge impact on reliability on performance. The problem we have there's two database gotchas that tend to manifest bad middleware, and very often the database is actually wrong at this point in time. The first one we're going to have to think about is how many people were here last year when we talked about redo logging? Okay?
Okay, let's run over that again quickly. So that obviously the redo log is a very critical part of any transactional system. Whenever you commit a transaction, that has to be physically written to a disk drive before your transaction commit is complete. So it's a very critical thing. If it takes a little bit longer, then what tends to happen is that a whole bunch of processes will back up behind it.
So what we're doing here is we're actually starting to play the same workload under a slightly different scenario. But what we have in the background is a background workload that is just beating the hell out of the disks. Okay? And it's making the log write times extremely slow. And I think maybe we're starting to see this show up on the right histogram down the right-hand side here. We're getting I/O times somewhere between 64 milliseconds and a second. Okay?
Right, so that's here, and we also see how that gets reflected in the log file sync times. Right, so there's multiplier that gets applied to each one of these. If it's taking very much longer than they normally take, gets reflected as tens or hundreds of slow log file syncs.
And then you get the next I/O storm arriving. As you can see, it's starting to creep in now. The transaction rate has dropped almost to nothing. And if you look at the response time, you can see that there's an amplification factor. If you're at the bottom of the middleware stack and you have an outlier of performance and you start going slow, it amplifies all the way up the system. So you'll notice we're getting thicker in blue as we go along. And as you get this amplification of if you're at the bottom of the stack and you're slow, it tends to multiply all the way up because it's basically a loosely coupled system. There's a series of queues pouring into each other. And if there's a delay at the bottom, it just manifests itself all the way up the stack. And you can see here, we've coded this to understand. You can see that even the CPU, when the I/O is stalled out, we can't even get the CPU busy on the system. Okay, we're just bringing the transaction rate to a halt.
Right, and you can also see that if we look up at the top on the right there, that the average log file parallel write time is about half a millisecond. So, you know, if you think, oh, well, we've got a problem with the logging IOs, if you go to the SAN administrator, he's going to turn around and say, well, your average IO time is half a millisecond. That can't be a problem. I mean, that's great response time. But then the reason that we're showing the data down here is that it's not the averages that are really causing you the problems. You only need a few of those outliers to really make for a bad day, right? Because of this multiplying up.
Now, in terms of solving this problem, you have a multitude of solutions to the problem. If you're not working on an Exadata system, basically isolating the disks that you do logging to is the obvious move. Make sure you're not sharing it. A number of times we see high log file sync times or log write times at the top of the hour, the half of the hour, when somebody's doing a checkpoint or they're synchronizing their Microsoft Exchange server on the SAN. There's something going off periodically that's forcing a lot of IOs on shared storage, because let's face it, if you're using a shared SAN, do you know what you're getting?
Yeah.
Do you know who you're sharing it with?
Somebody starts an Exchange server backup in the middle of your peak period.
We're
for the
sharing
database.
the same devices as your redo log disks. You can see, you're going to start getting these outliers. So, in many cases, just exclusive disks for the redo log is the answers. How many people have tried to fight with their SAN administrators to get exclusive disks and been told where to go?
There's some serious waving at the back now.
Right.
Yeah.
How many people found it easier to raise a PO for solid-state storage rather than fighting with your SAN administrator to put your redo logs on?
Yeah, we see this very commonly, that people will put SSDs in because it's so much easier than trying to deal with the storage guys and get exclusive devices.
For basic, you're getting exclusivity, and it's not the solid state, it's just the exclusivity. With Exadata, we're kind of neat. We get the cake and eat it because we have flash memory inside the devices. And you'll notice that Kai has just turned on the flash logging.
We've got flash logging turned on, and you can see that what's happened here is that even when, before Kai switched the screens there, you can see that we were getting a much steadier response time because we were using flash logging. So when the devices were really being beaten up by all the other workload, we were just writing to flash rather than writing to the disks using flash logging technology.
Yeah, and I think, if we'd had $1,000 every time we'd fix this, we wouldn't be here now. It'd be simple as that.
Yeah, there's certainly a number of Exadata customers that I'd work with who, when they moved to, 11.202 that had flash logging and turned on flash logging, large number of their OLTP problems went away just because of that steadiness of being able to consistently write the log file parallel writes.
Now, there's one other platform issue. Now, when we're allocating lots of processes, what else do we do?
Well, read memory, I guess.
We just chew up memory, like it goes out of fashion. How many people have heard the word huge pages on Linux? How many people cringe when I just said the word? How many people have sort of said, I don't think we need it?
Well, how many people use huge pages? Okay. How many people don't use huge pages?
How many people are
What
going
version
to
of Oracle are you running?
How many people are going to Google search huge pages while in the lecture, right? Okay. So, Graham, you...
Yeah, right. So let's talk about what we've got in this demo. So we've got two machines here. Each of the machine, even though one of them isn't using huge pages for the database, they're both using huge pages. They both have huge pages configured on the machine. That's because we use these machines for more than just this demo. Right? But one is configured with the database not using huge pages. Over on the right-hand side, we can see a number of pieces of information about the memory on these systems. And the one that's going to be key to watch is the memory free. Right, but you can see they've both got the same number of huge pages configured. We've got page table size over there. That's going to be another interesting one to watch. So at this stage, we've got a very small number of connections to the database, and the two memory profiles look pretty much identical. Right? What we've just done is we've upped the number of connections from 32 to 3200 and increased the think time from 2 milliseconds to 200 milliseconds. So we're applying exactly the same workload, we're just doing it through a larger number of processors now. So because we've increased the number of processors, we're going to have many more pages being mapped into memory. And we can see that the page tables, so that green stuff down there is page tables, is growing very significantly in the system that isn't using huge pages.
You may also notice that the memory free, even though all the connections are logged into the database, the memory is still, free memory on the machine is still dropping. Just by logging onto the database and connecting, doesn't allocate all the memory up front. You then have to start running some queries that are start kind of touching those pages, in particular the page tables, because why would you actually even allocate them until you touch them? Okay, so they're being allocated as you touch them, and you'll see, even though the guys are connected, and we got to the point at 0.5 megabyte of free memory, we fell off a cliff. Okay? The thing to note is what's happening to the CPU.
Yeah. Down here, right? So they were both going along pretty reasonably, fairly close together. Once we got out of memory, then you see there's a whole bunch of system CPU. It's got a page, it's got a swap, right? And that's what it's doing, and that takes over the machine.
And you'll notice the response time and the throughput of your machine is now extremely erratic, to the point that it just went down to nothing.
Yes, and remember, these two machines are both running exactly the same workload. The only difference between them is that one's running with huge pages, the other one isn't.
Okay, do you want to take some of that load off the system?
Yeah, so to try and get some memory back, what we could do is reduce the number of connections that we have to the database. So if we go down from 3200 to about 3000, so basically we're getting rid of 200 of the connections, you can see the free memory increases for a while. But again, as Andrew was saying, the use of memory will increase over time as your process touches more and more pages. So we'll start to see it go down again. So it'll go up, and then it'll go down, and then it'll hit 0.5 gigabyte again, and then we'll start paging again. So,
and just again, look at the reliability of the system. We bumped off 200 processors and it got reliable again. We're still using more CPU all the time, running with a non-huge page model. If you look at the pink line down the bottom, and we're just effectively waiting for that free memory to drop to 0.5 again. And
right.
You know exactly what's going to happen. We're at 1 at the moment. We're at 0.8.
Yeah, it's been going down gradually. We saw it go down from 1.5,
0.6.
1.
You know what's going to move
0.6. Do we guess that the next data point is going to be right down, or will we manage one more before it tanks?
Falls off the cliff.
There we go. 0.5.
It's so predictable. When it starts swapping, all bets are off. It's literally as simple as that, and then everything else falls apart fairly quickly, and you get interruptions. We can't emphasize, again, I think if we had $1,000 every time we fixed a system that hadn't got huge pages, how many number of times we've seen people they say, we sporadically just lose the system, the notes reboot, we can't even touch the machine, it's running 99% in sys. And I go, have you got huge pages? And they go, what's huge pages? And it just goes on and on. So again, it's on your tick list of things to get done. They're a pain to set up and size, but you can see in terms of system reliability and performance, it's just fundamental to get it right.
Right, and the number of major escalations that we've had to deal with. These are often things that have been going on for 3 months, 4 months, had lots of different groups involved, and then you look at it and you say, well, do you have huge pages configured? Oh, no, should we? Well, how about try it? And then suddenly the system's become a lot more stable.
Okay, so that really covers the things that we see at the bottom of the stack, bringing most systems to a halt and slowly. Now we're going to kind of focus on the middleware bit, because those are the things that usually the middleware blames. Okay? It's usually logging, it's usually memory. The next phase is actual programming. Okay? We're going to run a very simple test. How many people process batches of files into the database? Okay. How many people are Java programmers? Okay. How many people take a row, create a thread, process it, load it into the database? Suddenly got thousands of rows in my file, let's create thousands of threads. Okay? Again, it's happening all around the world where people are just shredding files by creating threads.
Well, the other way that it happens is that you get people write a service that processes one line out of the file, and then, okay, well, the file has lots of lines in it, and we want to run it quickly. So, well, obviously what we need is lots of threads, because then each one of those threads can be processing one line. And that will all work in parallel, and that's going to scale really well, isn't it?
Okay, so we thought we'd have a race. So what we've configured up a system is just a single process using an array insert versus a number of threads. We've got a total of 128 individual Java threads sharing a connection pool of 16 connections to the database. And let's see who loads the data first.
Right, so this is one process just doing array inserts versus 128 threads using a connection pool of 16 connections to the database. Trying to do the same thing. And we're loading 20 million records into each of these.
Okay, I guess it's not taking it long to figure out who the winner is. Okay, again, we wouldn't say this unless we see this every day almost of our lives, you know, of people writing one programs and then going creating 1 million threads in the middleware and letting a connection pool go to wall and try and load data or process late data or update data. Whereas a well-written program that I use an array or a set-based technique, you can figure out how much quicker it's going to be. What's the estimated times on these?
Yeah, so for the top one, the array one, the estimated completion time is just over a minute. And the one for the Java threads, 128 Java threads, is 22 minutes.
Okay.
So, 20 times faster.
Okay. It's interesting to look at the CPU profiles down the bottom. Which one used the most CPU? The slow one. So here we go. We've got less work done and we use more resources again. Okay? Same problem. You want to look at the insides of the database, Graham?
Yeah, and inside the database, well, we've got a whole bunch of waits for log file sync because each of our threads is inserting a row and then completing. That was the way that the service was written, right? It inserted a row and then committed. So a lot of time spent waiting for log file sync. So, well, maybe we weren't being completely fair there because we were limiting the pool size to only 16 connections to the database. We were talking earlier about having the number of connections to the database relative to the number of cores on the box. So, and we weren't fully using all of the CPU there, so maybe we can crank up the connection pool size. So now we've gone from 16 to 64, so we've given it 4 times as many connections, and we'll see what happens now. Well, we've got our estimated completion times there again. Obviously we didn't change the array one, so that's still around a minute. But we've reduced by 50% the time for the Java one. Now, remember, we could quadruple the pool size. That's not scaling very well, really, is it?
Yeah. It might be also interesting, Kai, if you could show us the CPU utilization on the application server as well. Because you might find that a little alarming. Okay? So, the threaded model is using more CPU on both database and app server. Just by virtue of just doing more stuff that isn't going to be the database processing. It's just doing more traversals over and over again.
Okay, so again, going up to 64 made some difference. Certainly didn't change the balance of things. But this was kind of an artificial test because we were inserting into an unindexed row, unindexed table. So I'm guessing that most of you who are doing OLTP transactions, inserting into tables, those rows probably have indexes on them. So let's see what happens when we run this again, putting an index on the table. Now, of course, we've got the difference between one connection doing our array inserts and 64 connections through our Java threads. So obviously the one connection can't contend with anything because it's just one connection. As opposed to that, we've got 64 connections. So 64 connections from the Java connection pool, can they contend with one another? Of course they can. They're all trying to update the same block in the index at the same time. So we're going to see a whole bunch of contention weights there. So probably buffer busy weights. Yeah, so as well as the log file sinks that we were seeing before, we're also getting the buffer busy weights now.
How many DBAs, when they see this, I know how to fix it, let's get some partitioning done.
Yeah, right, let's partition the table, we can hash partition it, we'll solve the
You know, it's like, I'm seeing all this
contention.
contention in the index, let's hash partition the index and, you know, do all sorts of goofy stuff with reverse key indexes. Did they ever at one stage look upstairs and see how the thing was programmed? Okay? Did they ever at one point in time say, time out, perhaps we can actually play the database a little better? How many times have you looked in AWR reports and find your top most executed SQL statement is coming in at 2 million times and it's all sub-millisecond every time? Yeah. Classic row-by-row processing. The problem is when you do it row by row, when you multiply by a big number times a small number still equals a long number, big length of time. How many people have a problem with their batch windows? A lot of people. Okay.
And you know, it's most frequently when people have a single row service that they're then trying to use in a batch mode. And there's no reason why, as part of your service, you shouldn't have an array mode. Right? We've been trying to teach this to people for years, and it just doesn't happen.
We're kind of rolling.
We'll try and take questions at the end, but we've got a lot of demos to get through.
We're on a mission here.
Yeah.
Okay. So you can see just the simple programming techniques can get you into trouble from the beginning. And everyone says, well, this is a ludicrous example. I saw it a month ago in a bank, and they couldn't load their transactions overnight. And it was all the database's fault. You know, and I said, well, why don't you just do an array? And then it was like, oh, got it. You know, oh, I can't change my code. It's impossible to change my code. I said, well, I don't think you can afford not to change your code. And again, people at the bottom of the stack, the DBAs, need to learn to articulate it. You need to articulate the problem you're seeing. Okay, it's extremely important. Okay. We're going to move on to the next phase, which is more in the realm of the system architect. And this is something that we see both with OLTP systems and in these batch systems. So perhaps, Graham, you'd like to describe what we've done now. We've taken that little programming problem and multiplying it up to a full enterprise infrastructure.
Right. Yeah, so we have a situation here where we have files coming in from some part of the business. Now, these files can consist of things like transactions that have line items. They could be data from telco switches. They could be from manufacturing, production, where we have a whole bunch of tests coming from a particular run of a product and things like that. So the data comes in to our system.
They could even be your tax records.
Right.
They could
No, surely not, Andrew. So the data comes in as files into the system, and then we have an architecture which is designed to load balance to use all of the resources that are available on this system. Right? So we paid for all this kit, so we want to make use of it. So each file is spread across and processed across a number of different application servers. So these things here are our application servers. And within each application server, we're running a number of threads that are connected to the database. And they're connected to the database through, in this case, a scan listener, which distributes the load across multiple instances of our rack database. So although these things are drawn as two separate disks here, they're really two separate computers with one shared disk. So that's a rack system there for you. So you can see what's going on here in that each file is going to multiple application servers. Each application server is doing transactions against each of the instances. And if you're watching this closely, you'll see that occasionally these things are moving along. I've seen jog a couple of times here.
So the system architects have been completely effective in getting perfect load balancing. They've achieved perfect load balancing on the system. The big snag with this perfect load balancing is it's kind of slow.
Yeah, so we're getting around 3,000 transactions per second through this. We're queuing in the application, okay, not necessarily a bad thing. But if we look at what's happening in the database, well, there's not much CPU down there, right? That's the green bit at the bottom. CPU's pretty untroubled by this workload. We have some TX contention down there. We have buffer busy waits. But then all this grey area here is all rack waits. Now, I don't know about you, but the amount of CPU that we've got down here is tiny compared to either of these machines that we're running on. So it seems like we could easily handle this entire workload in terms of CPU requirements by just running on one of the nodes. And if we run on one of the nodes, then all those rack weights are going to disappear, aren't they?
This is kind of a more brutal approach to tuning, by the way, of elimination of weight events.
Elimination of an entire class.
We're not saying this is the suggestion, we're just teaching you going through the debugging cycle, because we go through this as part of our daily life. So we've rerouted all the work now to a single instance.
Oh, and now we can clearly see that the data flows here are animated, right? We couldn't see it so clearly before because it was a lot slower. Now we're up to running around 24,000 transactions per second. So we've gone up almost an order of magnitude by running against one instance rather than two. Okay.
That doesn't come with the marketing, does it?
No, right.
All
well,
right.
So maybe we're onto something here, though, because certainly in business terms, we're running a lot better now. Right? And what we did was reduce the contention by running against one node rather than running against two nodes.
We still seem to have a lot of contention even with a single node.
Yeah, there does seem to be a lot of contention there.
I'm not even convinced you're getting one node busy properly.
Right. Yeah, and the CPU down here is still significantly lower than the resource that we have available on one node. And then there's a lot of contention. The contention was TX contention, buffer busy wait contention. So
the DBA is, what do we do? Oh, who dare say partitioning and reverse key indexes at this point?
Reverse key indexes? Wash your mouth out.
Right. Okay.
Right, so
everyone's going to Google it. Oh, contention, well, I better have partitioning and reverse key indexes. Right.
But if we go back to first principles here and we think, well, how are things contending? We've got a file which we're passing through an application server and it's going to the database. Right? So how about if we had affinity between files and database? So if we had this one file was always processed by one of the application servers. Right? We've got hundreds of thousands of these files coming in. So we don't need to use the entire resources to process one file. The application server can take on many files. So if we use affinity between the file and the application server, what happens then? Well, because we've now got less connections to the database applying transactions from an individual file, we've now reduced the amount of contention that we have in the database. Right? It's pretty easy to see, and it's been reasonably effective. We've got another bump in performance there. Right? So we're now up to 44,000 transactions per second.
Yeah, we're starting to see logging coming in more, but we've still got a lot of brown now.
Yeah, now, so obviously we're putting each file through a single application server now. Well, these files are relatively small.
And then let's just start also thinking about those files. These could be a file that has a part serial number, and then each step in the measurement process could be your social security number and every tax line in your tax form. Okay? It could be things coming off a switch and a number of phone numbers. It could be you checking out at the supermarket, your transaction going through on every line that you just swiped on the point of sale system. It's very real world stuff.
Right, so if you've got, your basket has gone through the checkout and there's all your line items there, well, why not make that affinity a little bit more? So rather than just using the same application server, why not use the same thread? So that each basket that's going through uses the same thread. Again, we're going to get back to the situation that we're not going to get contention for the index because it's the same thread that's doing it, and it can't contend with itself. Right? Now, this doesn't change the picture here in any way other than that the lines move faster, right? So there isn't a graphic difference for this, but you can see that now we're up to around 70,000 transactions per second. Remember, we started with our beautifully load-balanced system that was running at 3,000 transactions per second, utilizing all of our application servers, utilizing both nodes of our rack system.
And we actually know we're starting to hurt the system a little bit because we're getting some of those wait events we saw when we were oversubscribed, overprocessed to the machine. Because you can see that we're nearly at best one of 16 processors runnable on the CPU. So
right.
You're going to expect to see a little bit of latch.
Right, so the green here, now we are starting to max out the one node that we're running against. So how are we going to make it faster still? Well, maybe we need to do something with that other node. But instead of doing it through the way that we were doing it before, and using the scan listener to spread the connections equally across the multiple instances, what we're going to do now is we're going to apply affinity between the application servers and the instance. So each of our application servers is connected through an exclusive service to an instance of the database. And remember, these are machines and it's shared disk still. Right? So this is still running against rack, 2-node rack there. But now we have affinity all the way through the process. So a line in a given file is always going to be processed by the same application server, the same thread in the application server, going to the same rack node. And so we're now going to get no contention there. So this is now all log file syncs. And now we've gone from one node to 2 nodes, and what's happened to our performance? Looks like we've got up to nearly 130,000 transactions per second.
Okay. So you can see, just getting me thinking, we didn't do any partitioning. We didn't do any funny indexes, the same structures.
We haven't changed the database at all. We changed no parameters.
The only thing we have done is control how we direct the stuff coming out of the file. Now, the file and the batch processing is the more extreme case, because the data's coming at you and you're against the clock to get in the middle of the night. Okay? We've also seen a situation where people have mapped basically their browser or terminal ID to go through to the same thread in their middleware. Very often they keep a little bit of state in their middleware. So if you map it all the way through, you're going to get affinity all the way through. So if you're working with one customer ID and he's logged on and making an order, the fair chance that the affinity goes all the way through the middleware, he's going to find the blocks he just read in the buffer cache are still there. He's not going to have to suddenly find that he's being load balanced to another node in the cluster and have to reread them somewhere else. Okay? So for OLTP, it has this impact of crispening up the response time and making it a lot more sharp, because you're not doing so many remote buffer transfers. But in batch, because you're not moving stuff around, it allows you to really get the wall clock time, or the number of things done per second.
Yeah, so you're just greatly improving the efficiency of the system.
Okay, and so you can see we've now got this system running well, but we have to pay attention to this affinity at all layers in the stack. Okay, what happens if you have two organizations that don't talk to each other? There's been fantastic affinity built into the middle tier. The application developers have got fantastic affinity either through files or from browser IDs down to individual threads. Once if somebody says, oh, I think it's a good idea we have a round-robin listener, let's see what happens now. Everybody in the organization has to buy into the affinity concept. All right?
So, and as soon as you lose that end-to-end affinity, you're going to lose a lot of performance. And this is one of the problems that we have working with customers trying to get them to implement this, is that they may implement it in part of the system and see maybe a small improvement in performance, maybe no improvement in performance. And then they say, well, it's not really working for us, is it? Well, all that they've done is just move the bottleneck to the next part of the system that was being load balanced and spread. Right? So you really do need to have this affinity right through the system for it to work for you.
And this is a common problem. And the thing that is really scary, we find out about it after people have been developing the system for 3 years. Okay? And you become victim of system architects who basically are really good at putting acronyms in boxes, but actually don't think through the data flow process. Okay? This is people who are out of touch with what's going on. You know, for everything to work fast, it needs to be in memory and local. Now, you only need to, when we had a fully load balanced situation, the stuff was in memory 50% of the time. Probably in this case, we shifted it up to about 90% of the time. You'll never get a 100% solution. But by shifting it to being local memory from 50 to 90 to 95 to 99% of the time, you're getting the performance back. And I think Kaya's
just busy destroying the system again.
You can imagine all those war room meetings saying, let's load balance more afterwards, after we had a successful system. We successfully detuned it back to where we were. And you can see the transaction rate. So, don't wait 3 years to find out you've got this problem. Please.